Around a month apart, the twin Voyager space probes set off on their historic interplanetary mission in 1977. In 1989, only 5 days after the 12th anniversary of its launch, Voyager 2 was the first and only spacecraft to sail by the planet Neptune, which circles the Sun at a chilly 2.7 billion miles. The distance between Voyager 2 and Earth has only increased since then, currently traveling at a speed of 34,000 miles per hour beyond our solar system. 2018 marked the journey of Voyager 2 beyond the boundary between our solar system and interstellar space. More than 41 years after its launch, even if the Voyager has no more planets to discover, the probe is still on its multi-decade journey over space's vast and uncharted depths. Welcome to the Technology Zone, where the home of technology resides. In this video, we will talk about what the Voyager learned on the way. Which one has the best chance of traveling the farthest across the cosmos? But before we get into the video, consider giving this a thumbs up and subscribing to our channel as we assure you this is worth your time. Nearly 20 billion miles away from Earth at this time, more than 200 times the distance or range between the Sun and the Earth is where the Voyager 2 is. Voyagers 1 and 2 departed their homes around the same time. However, because they are traveling in opposite directions, they are now farther distant from one another than they were before from Earth. Amazingly, both probes are still in a functional state after 40 years and frequently send fresh new data back to Earth for examination. The power source that Voyagers use is the key to their long life. 3 RTGs or radioisotope thermoelectric generators containing a small quantity of plutonium are affixed to each probe. The spaceship systems are powered by converting the heat from radioactive decay into such a usable electric current. The plutonium fuel the Voyager uses has a half-life of about 90 years, making it perfect for supplying energy for a considerable amount of time. The fact that the Voyagers have survived for so long has been highly beneficial to astronomy. For a very long time, we might not have had the opportunity to research the unknown that exists past our solar system without these 2 probes. These Voyagers found that a massive cosmic bubble, the heliosphere, encircles our Sun. Additionally, astronomers found that plasma from the solar wind, which originates from the Sun, fills this bubble. On the edge of the heliosphere, there's a part where the solar wind and the interstellar medium clash, and astronomers call it heliopause, or it is a term for the heliosphere's outer border. Before the Voyager's launch, one of the main issues in astronomy was the heliosphere's composition. Even its size was unknown to scientists, and some even hypothesized that it might be situated almost beyond Jupiter's orbit. Although it was obvious that the boundary of the heliosphere was considerably farther away, as Voyager 2 flew through Jupiter, Saturn, Uranus, and eventually Neptune, no one knew with certainty when Voyager would reach it, or even whether it really would before Voyager ceased to function. How about you guys? How big do you think this heliosphere is? Drop your answer down in the comment section below and we'll see who gets it right as we proceed in the video. Well, here's to answer the question. In 2012, Voyager 1 noticed that the solar wind was beginning to diminish and that the particle density surrounding it had significantly increased, suggesting that it had crossed the threshold into interstellar space. A few years later, Voyager 2 felt the same manifestations, which officially indicated it breached the heliopause effectively in 2018. The heliopause border was determined by both spacecraft to be 120 astronomical units or AU, or 120 times further from the Sun than the Earth. However, many astronomers were shocked that Voyager 1 and 2 both passed the heliopause at about the same distance. Solar activity, flares, and sunspots change in a predictable pattern during the course of the Sun's 11-year cycle. Astronomers had predicted that during a solar cycle's peak, the solar wind will put even more pressure on the heliosphere, causing it to expand like a balloon, and that this pressure would subsequently decrease during the cycle's calm periods. From 2012 to 2018, the Sun's activity has grown. Therefore, when Voyager 2 analyzed the heliosphere, it should have been quantifiably greater than when the Voyager 1 did. However, the fact that the twin probes obtained virtually identical distance readings indicates that the heliosphere is significantly more durable than previously believed. The interstellar medium itself is the cause. The region between stars is filled with a faint but detectable magnetic field. This interstellar magnetic field was measured by Voyager 2 to be roughly 7 microgauss. For comparison, that is 64,000 times weaker than that of the Earth's magnetosphere. Even yet, the 7 microgauss is almost twice as powerful as what astronomers had anticipated. The heliosphere is under enough strain from the unusually powerful interstellar magnetic field to maintain a pretty much constant size throughout the solar cycle. Even more unexpected findings have been discovered by Voyager 2 as it traveled into interstellar space. The plasma wave research instrument on the probe revealed only a year ago that the density of the interstellar medium is actually rising as it moves farther away from the Sun. According to Voyager, the particle density of the surrounding space has already increased by more than a factor of 2 during the course of about 20 astronomical units. This sharp density gradient is surprising and has no known cause. According to one theory, the interstellar particles slow down as they get closer to the heliopause, building up like a traffic jam in the area where Voyager is currently passing. Another hypothesis or theory that the magnetic field lines actually get compressed when the interstellar magnetic field collides with the Sun's heliosphere, driving ionized particles away and producing a comparatively depleted zone between the heliopause and the remainder of the interstellar medium. Which of these theories, or any variant of both, is correct may be ascertained when the Voyagers go farther and deeper into deep space and gauge the interstellar medium's density. Sadly, we might never learn the solution. The Voyager's plutonium energy sources are deteriorating with time, and just how much further they will be capable of working is undetermined. But before the Voyager becomes completely quiet, it will keep gathering new data from the furthest reaches of known space. It discovered yet another intriguing revelation early this year. The interstellar medium was producing a faint humming noise. Vibrations can travel through the unstable plasma of outer space, much as airborne particles transport sound waves. Even with the use of the Voyager's sophisticated antennae, the sound would be too weak for your ears to pick up because the interstellar medium only contains a few particles per cubic centimeter. Astronomers have waited a few years to hear this odd disturbance. Immediately after Voyager 1 passed through the heliopause, it picked up a string of relatively loud, high-pitched whistles. These sonic bursts were fleeting like a shock wave cutting through the tenuous interplanetary plasma. Moreover, the brief surges of activity on the Sun that caused these noises have been connected to them. The Sun's activity causes space to tremble like a stone thrown into a pond. These explosions occurred at a convenient time. Because it made it possible for astronomers to measure the interstellar material more accurately than ever before, they only provide a brief glimpse into what is going on and only display the consequences of sporadic solar explosions. What occurs between those signals is what astronomers are most interested in learning. They would better understand the interstellar medium's absolute density and how it changes over time with continuous measurement of it. A team from Cornell University ultimately discovered what they were hunting for in May 2021. The scientists found a novel sound by analyzing data from Voyager 1's plasma wave science antennas, a lengthy, steady hum that oscillates in the 3 kHz range. If we could hear this could sound like a single constant note played continuously but shifting very little over time, according to Stella Oker, a vital member of the Cornell team. Now, astronomers don't need to wait for a random occurrence to measure density. Astronomers can now practically continually monitor the density. This recent discovery of interstellar noise represents a significant advancement in our knowledge of the nature of space beyond our solar system. Astronomers will be able to comprehend the interplay between the sun's magnetic field and the interstellar one by utilizing continuous observations from Voyager. And what transpires at the point when the solar wind and interstellar plasma converge? Perhaps one of astronomy's biggest and most fascinating mysteries to this day is the distance between the stars in the Milky Way. Some of those questions may be answered by Voyagers 1 and 2. However, it's uncertain how much more science they would be able to do because they could only be functional for a few more years. Unsolved mysteries could continue to exist. Well, at least until a different probe can be dispatched for the countless years-long journey into interstellar space. Well, this may be the end of today's video, but this is not the end of the Voyager's journey. If you want to get more content like this, consider subscribing and hit that notification bell so that you will be notified in our future videos. Who knows, you might have a chance to hear more amazing findings of the Voyager's discoveries out there. Again, this is Technology Zone. See you guys in the next one.